Today my talk is on the inference sampling for general linear models. It is very related to the previous two talks. So this is joint work with Michael Mahoney, Peter Joynis, and Professor Bing Yu. So where is the pointer? So my talk will have these three components. First, I will give an introduction and overview of the sampling problems. And then I will talk about the inference sampling for least squares. Finally, I will say something about the sampling scheme for generalized linear models. Okay, first, this is a motivation of the sampling problems. Now, let's consider a very big problems. We have a lot of observations. So we try to solve a very big linear equations. So the best way to estimate the linear coefficient is via the least squares. So if you have a lot of data, now you do not want to use all of the data. So we try to sample a few of them. If we sample them, then we can try to solve with least squares. Here, wi is equal to 0 if some data points are not sampled. If one data point is sampled, then the w is not 0, and we also give that point some weight. So the goal for this sampling problem is to construct a good w such that this new problem we call the sub-problem, because the number of data points used for solving this least square problem is much smaller than the original problem. So we call it a sub-problem. So our goal is to design a sampling scheme. We call this W such that the solution of this sub-problem is very close to the solution of the original problem. So for the least square, there are now many works for the sampling schemes. So it's well known that Joynis, Mahoney, and other researchers developed the leverage score sampling. So now let's have a quick review of the leverage score sampling. So what is a leverage score? Leverage score is so you have the design matrix X. So in statistical language, the leverage score is just the diagonal elements of the height matrix. So if you are not familiar with the height matrix, you can also do the SVD of X. The left single vectors of X is U. So the squared norm of the rows of U is just the leverage score. So the leverage score sampling, this is a leverage score sampling procedure. So basically speaking, we randomly sample each data point with probability proportional to the leverage score, and then give a weight. The weight is equal to 1 over square root of R times the probability. Okay, here R is a number of data points we want to use. And then we solve this with this square. So here the W, you can see that the Wi is equal to 0 or non-zero. If it is 0, it means that the data point is not selected. If it is non-zero, it means that that data point is selected, and we give a weight. So the theoretical results show that if the number of data points we sampled is like this way, it is equal to P divided by epsilon times a log term, and the P is the number of columns of X. I use N to denote the number of observations or the number of rows. So this theorem says that if R, the number of data points we sampled, is about P over epsilon, so it has no relationship to the number of observations in the original problem, then this is the fitted value or the L to error using the the parameter estimated from the subproblem. So this error is very close to the original error. So this is a review of the leverage score sampling. So we all know that leverage score is a concept used in robust statistics. It is a criteria to see if one point is likely to be an outlier or not. There is another criteria to see if one data point is an outlier or not. It is called influence score. Let's see an example here. We see that there are some data points which might be outlier, or it might have very big influence to the linear equation. You see this data point has very big influence, and this data point is also has very big influence. But for these two data points, we see that the leverage score is small, because the leverage score, in fact, it only depends on x, does not depend on y. So if a leverage score is big, it means that that data point is very far from the center of the data points. And we see that this data point, this called I or 1, this data point, in fact, it has very big leverage score. But we see that this data point has almost no effect on the linear equation estimation. So for this point, we see that it is not an outlier, or it has very small influence on the estimation of beta. So probably we should use the influence score as a way to sample the data points. I mean, if the influence score is big, then we should sample the data point from the original data set. So, so what is influence score? In fact, there are a lot of definitions about influence score. One definition is the leverage score plus the normalized residual. So you can see that if the residual is big, that means that the data point might have big influence. So this is one definition of the influence score. In fact, this influence score has a very close relationship to the leverage score. So if we define the extended matrix as the design matrix X, and then another column of the observations, the responses, this Z is called extended matrix. The leverage score of the extended matrix, in fact, it is equal to this influence score. So now we just use this influence score as the sampling probability. It is very similar to the leverage score sampling. The only difference now is that we use the influence score as the sampling probability instead of the leverage score proposed before. And now we can also prove that, so if the number of data points we sampled is bigger than a constant times p over epsilon, then the estimate from the subproblem is very close to the estimate from the original problem. Okay, the previous result is about the least squares, and recently there are developments about other models, say the L1 regression model or the LP regression model. The L1 regression is y minus x beta L1 norm, and also the sampling scheme is also proposed for the quantile regression problem. And today, I'm going to propose a sampling scheme for the generalized linear model. Let's first have a quick overview of the generalized linear model. So a generalized linear model consists of 3 components. The first is the probability distribution, the conditional probability distribution. Usually, people use this distribution as the conditional distribution class. It is called extended exponential family. It is a little bit different from exponential family. Anyway, this is a very common distribution class for the generalized linear model. And another component for a general linear model is a linear predictor, because it is a generalized linear model, so we have a linear predictor. And to connect the distribution class with the linear predictor, we use a link function. So this link function connection connect the expectation of y and this linear predictor. So this is the generalized linear models. So if the link function g is chosen such that the g expectation of y is equal to theta exactly, then we call this g a canonical link function. And also there is a very good connection between the expectation y and this function b. We can prove that the expectation of y is equal to the first derivative of b theta. Okay, to solve a general linear model, we can use a maximum likelihood estimation. So the log likelihood function of a GLM is this. And because usually the psi has nothing to do with the beta, so the maximize the likelihood estimation of beta can be solved via this equation. So here we can see that the b plays a very important role. And if you choose b is equal to, if the b is a quadratic function, then this estimator is just the least square. So if b is equal to this log 1 plus exponential of t, this estimator is a logistic regression. And if b is just the exponential function, then this estimator is a Poisson regression estimator. So this model contains a few other models. We call it the generalized linear models, including the least square. Okay, now we want to solve a very big general linear model problem. And the way we want to do is the same as the least squares. We want to sample the data points. If it is sampled, then we give a weight w. If it is not sampled, this w is equal to 0. So this is the sub-problem. Our goal is that we want this the estimate of the sub-problem. Okay, this should be beta tilde. Okay, we hope that we after we give a few very good design on the w, this beta tilde is very close to the beta hat. The beta hat is estimated from the original data. So this is a very simple, okay, the very first result. So we say that if the W is constructed by the S transpose S, in fact, this S is a sampling with rescaling matrix. So if the W or S satisfies the two equations, 7 and 8, then we have that this the estimate of the estimate from the sub-problem is very close to the estimate from the original problem, but we need the very strong condition. We see the strong convexity condition. It means that we need the objective function or the likelihood function, or log likelihood function has a strong convexity condition. This condition is, in fact, is very strong. At least for logistic regression, usually it does not hold. So now we see that the condition 7 and 8, it only depends on the x, does not depend on y. And these two conditions are also needed for least squares. So as long as this sampling matrix satisfies 7 and 8, in fact, you can use the Levy-Score sampling. The Levy-Score sampling satisfies 7 and 8. So this result says that for generalized linear models, if the strong convexity holds, then you can use a Levy-Score sampling and it gives very good approximation of the original problem. Now we want to remove this very strong condition. Now we try to see that how the weighted list, how the generalized model, how people estimate the parameters in the weighted list in the generalized linear models. So usually people use iteratively weighted list squares. Basically speaking, it is a Newton-Raphson method. So you can see that the update using Newton method is equal to, it can be derived this way. It is a iteratively weighted list squares. So for each iteration, you have to update this weight and also update this response y. The x is not updated. So now you can see that for each iteration, it is a least square problem. And so in each iteration, you can use the level score sampling or the infinite sampling to solve this big data problem. But the problem is that this weight changes in each iteration. So every time you have to calculate the level score. Now we propose a new method. We do not have to calculate the level score in each iteration. So the method we propose, we are using the weighted level score as the sampling probability. It is defined as the weight times the left single vector, the rows of the left single vector. So if we something this way, then we can see that for each iteration in the iteratively weighted list squares, we just have to update this score. It depends on the weight and the original leverage score. So we only have to calculate the leverage score once and then update for each iteration. So this is the theoretical justification. We see that if the condition 9 and the condition 10 hold, then the solution for the subproblem is very close to the original problem. So for condition 9 and 10, we show that if we use the weighted level score sampling, then with high probability the two conditions will hold. Okay, this is main content of my talk. I first show how do we use the infinite sampling for least squares, and then I show how to use the level score sampling for the generalized linear models. But for this problem, we need a very strong condition. Usually the condition does not hold. To overcome this problem, then I propose the weighted level score sampling. And for this sampling, we use iteratively weighted list squares, but in each iteration, we do not have to calculate the level score every time. Okay, this is my talk. Thank you.